Hello everybody. Back to Introduction to Digital System. Today topic is magnitude comparator and multiplexer. Okay. Now we are going to discuss two things: the magnitude comparator and the multiplexer. Magnitude comparator, we will compare. Okay, compare two bits, two binary numbers. Okay, 4 bits, and we will create single comparator, and we will see the pattern of operation. Also, multiplexer, or let me say data selector, it's like a switch, selecting a switch. Okay, we will select one data from several data, or one bit from several bits. We'll see the input, how we use, how we select, and the implementation of logic circuit. Let me start with the first topic, which is magnitude comparator. As you know, comparison is one of the higher way of thinking, and in computer we need it to check to compare between data. Let's take a simple example, comparing between two numbers, A and B. I mean, either A equal to B, or A greater than B, or A lower than B. How we can do this? This is what we are going to discuss in this part. We'll see the design. By the way, it's reflected, comparison reflected on many operation and processes inside the computer, and they have many applications in industry, and it's reduce the design effect, reduce the human error. Let's take example. See here, I have two numbers, A and B. A and B. I want to compare between them. Both of them are 4 bits number. It means it will be A, as example, 0, A1, A2, and A3. Okay, three numbers. Okay, and the same thing, B0, B1, B2, B3. I want to compare between them. This is magnitude of comparison, to come up with the results, which could be either A lower than B, or A equal to B, sorry, or A greater than B. These are my results of comparison. How we execute this, or how we make a diagram. Let's assume that we want to build a logic gate diagram to compare between A and B to see if they are equal. Okay, what I will do, I will use XNOR gate here, 4 XNOR gates for the 4 bits. You see here, A0, B0, A1, B1, A2, B2, and A3, B3. And just to remind you that XNOR, these gates, the 4 gates, XNOR, okay, it give high or 1 as output whenever the inputs are equal. It means when here A0, B0 are either 0, 0 or 1, 1, the output will be CO, which will be 1. Let's assume here it is 0, 0. Then here will be 1. You see? Let's assume they are 1, 1. It will be also 1. The same thing could be say for A1, B1, A2, B2, A3, B3. And you see here we have AND gate, so it's multiply. At the end, if it is 1, then here will be 1. And definitely here will be 1, here will be 1. All of them, if they are equal, then the output will be 1, because it's multiplication. Now assume one of them is not equal, then 0 will come. 0 will come here. As example, here we have 0, 1. The output will be 0, and the output here will be 0, and the output here will be 0, which doesn't mean that it is not equal. You got it? So it's very easy. We use XNOR gate and AND gate to produce magnitude comparator. This is if it is equal. What if it is greater than or lower than? Greater than. And taken in consideration that truth table is good up to 2 to power 8, which means 256 states. Now, for comparison, to make sure that A greater than B, what we will do, have a look, a little bit improvement. Let's assume these are two numbers. A is 1001 and B is 0111. I'm start reading from the left, otherwise it should be from the right. Okay, now you can see here we have 9, okay, and here we have 7. So 9 greater than 7 is clear. But why 9? Because this is 8 and 1. And why 7? Because this is 1, this is 2, and this is 4. So altogether 7. Okay, we know that A greater than B. Now what we will do, we will make the comparison starting from the most significant bit, I mean from the last one to the left. You see, you compare these numbers. By the way, we have digital, we deal with binary, so we have two digits, 0, 1. 1 greater than 0, done, right? 0 equals 0, 1 equal 1, but 1 greater than 0, clear? 0 lower than 1. So always we started from the last number or bit to the left. So A3 dot B3 dash, and this now equal 1. So if I use AND gate, I will come up with 1. This tells me that the A is greater than B. So don't forget, we started from the last number to the left. Okay, so AND gate here will be enough to give me high, which tell me that A is greater than B. Now, this is not what happened is, what if, I mean, the previous example, it's directly, we compare the last number to the left, done. But here in this example, you see 1 here is equal to 1 here. So 0, I go to the next weight or next order bit. 0 is equal to 0. But 1 here in red is not equal to 0. You got it? So A greater than B. What should I improve to make sure that it's correct? I do it like this. I started from, as I mentioned, the left, A3, B3 dash, to make sure that A greater than B, to check this option. Plus A2, B2 dash, but I will multiply by C3, which is the output of the first expression here. And I go more, as example here, it will be C3, C2, A1, B1 dash, and so on. We want to multiply in AND gate, multiply by the previous state to make sure that it has been approved and we can go and move to the next one. Because if we don't consider this, what will happen is taking this expression directly, it could mislead you. Okay, it could say that example it is greater while it is not. Okay, so we need to consider the previous state. Okay, as you can see here, I wrote it. Okay, as you can see here. Now, to summarize here, we will say that logic to algorithm, algorithm to logic. What we have is four bits, A0, A0, A1, A2, A3, and B is B0, B1, B2, B3. And we have four options, either they are equal, A greater than or less, for equal, it's supposed to be all identical place or order. Numbers should be equal, bits should be equal. It means A3 equal B3, A2 equal B2, A1 equal B1, and A0 equal B0. And this equality represented here, either xi will be ai bi plus a dash I b dash I. Okay, if they are 1 1 or 0 0, this means they are equal. If we find for each state, for state number 1 0, state number 1, state number 2, state number 3, the output multiply, so it means OR gate and gate. If it give 1, then this means that A equal B. The difficulty happened when A greater than B or A lower than B. And we put expression here which say that A3 B3 dash, I'm comparing, don't forget, A greater than B, plus A2 B2 dash multiplied by the output of the previous state, plus A1 B1 dash by the output of the two previous states, plus A0 B01 by the output of three previous states. The same thing could be, say, here for A lower than B, just we change the complement. Rather than it was on B, it will be for A. Okay? And if we go to the market, we will find there is chips ready used as a comparator. One of them is well known, which is 74HC85, as you can see here in blue. and it compares between two numbers, okay, 4 digits, as you can see, A and B, from A0, B, A1, A2, A3, and B0, B1, B2, B3. And the output is three options, either A greater than equal to, lower than B. This is another, okay, shape. Show you that these are my inputs, A's and B's, and here my outputs, A equal, lower than, or greater than B, and here is the cascading inputs to check the situation of A and B with respect to each other. Here, comparing it to inputs, you see here A3, B3, A2, B2, A1, B1, and AO, BO. And usually we started with, say, from the last number. As you can see here, with two options, either A3 greater than or A3 lower than. Okay. Now when we compare it, you see here x, 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 because we don't go to the next level unless we make sure that they are either greater than or equal than. If they are not, then this means that they are equal. The output, if A3 greater than B3, the output will be high here on the option which say A greater than B. If it is not, then, by the way, low, low. If it is not, it's A3 lower than B3, then the high will be for A lower than B and the others will be low. By the way, high and low mean 1 and 0 respectively. And if this is not give me solution, we go for the next one. This means that they are equal, and we go for the next one, fixing A3, B3 are equal. We go for the next level. You see here, this is the next level, and again we check high and low for A and B and so on. You can apply this and check the truth table how it work. You see, I'm changing the numbers. Now the input number, binary number, is 111 and the other one is 0110, which tell me that A greater than B, then this mean high. Now 011 is 7, 0111, which is 7, they are equal, then the output is A equal B. In this way, you see, it compare digits from the left to the right and check if they are equal, greater than, lower than, and then give decision. So in this application, as you can see here, let's assume that the temperature on the furnace is 80 degree, okay, which is equivalent to the number here, whatever it is, okay, it's reflecting the 80 degree. And the temperature sensor mentioned here for this, which used to measure the temperature inside the furnace, the temperature sensor here is represented by A. This is B and this is A, as you can see here. Let's assume that the temperature was 78. Okay. Now what happened? Because we make a setting through the keyboard here to have this temperature, comparison will occur through this magnitude comparator. You see, here we put lattice just to send the output signal. We'll talk about lattice in the next few topics, but here to say that if the temperature, okay, which is B, 80, higher than the number A, which is the temperature sensor of the furnace, then this means that we send signal to the furnace control to say increase the temperature. Let's say it is increased, it become up to 80. Then if it is up to 80, they are equal. Okay, no signal sent. Then keep quiet, keep the furnace temperature as it is. And then if the temperature increase become 82, this means that the number A become greater than number B. So the signal came now to say that A greater than B, furnace should reduce the temperature. Temperature should go down because it's higher than the required. You see, this is one application in industry. Now the next topic in this the next part in this topic is multiplexer. Multiplexer simply is, let me say, a logic circuit which used to select one input from different inputs. It's simulating selecting the switch. You can see here as example in this is just example multi-data input, and this is selected switch, and this is one output. You see here it's in red, it's mean it's selecting IO. If it is become here, it means it's selecting I1 and so on. It's let me in general we have here parallel. Let me write it. Okay, parallel input and serial, one serial output. Okay, so we select them to appear in a serial way. So the inputs are many inputs in parallel, and the output will be just one output. Example here for logic circuit, let's assume we have 2 bits here or 2 digits here, IO and I1. Now S is the selecting, okay, condition, so it's either 0 or 1. Now here we have sum of product 2 AND gates connected through OR gate. Okay, let's assume we have 1. Then here it's 1, here it is 0 because there is inverter. You see, this means that IO, whatever it is, it will appear here. IO, sorry, it will be 0 because it's multiplied by 0. But here I1 will appear, whatever it is. If it is 0, 0, if it is 1, 1. And at the end here I1 will appear. You see? Let's assume the opposite. Let me take another color. Okay, here 0, here 0, here 1. Nothing will appear here, but here IO will appear. And at the output, it will appear IO, whatever it is, 0 or 1. You got it? Now, this is multiplexer, or simply they call it mux. Okay? Transferring the data, okay, if it is they are parallel, and transferring them into one. You can represent it here by this block diagram. Okay, these are my inputs. These are just 2 inputs for as a start to the discussion, and this is the selecting switch, and this is my output, which is one output. Now 4 to 1 line multiplexer. 4 to 1 line multiplexer is, you know, we represent digits, numbers by 4 digits, okay, 4 bits. As example, D0, D1, D2, D3. And we need here 2 switches, okay, because, you know, 2 to power 2, it will give 4, and we have 4, as you can see, D0, D1, D2, D3. Now the output, okay, is sum of product at the end. Here we have AND gate, as you can see here, 1, 2, 3, 4, for each one of these digits, which is connected to OR gate, as you can see here. Okay, we need S0, S1 to simulate 0, 1. Okay, so S, it could be 0, it could be 1. So the options I have for S1 and 0 is 0, 0, 0, 1, 1, 0, 1, 1. Okay, and it's connected. It's connected here. Let's take the first situation when it is 0, 0. S is 0, 0, 0 here and 0 here. Okay, what will happen? You see, here will be 0. Then the output here will be 0, regardless what is connected. And here will be 0. Okay, and here will be 0. But because of these 2 inverters, here will be 1, here will be 1. So DO here, whatever DO will be, it will appear across the output DO. You see? And appear across the output here DO. So DO, because of the state. If it is 0, 1, you can see here D1 will appear, as you can see here. If it is 1, 0, D2 will appear. So it's like a switch. Here is selecting a switch to say that which one of these bits will be at the output. Now, 2 to 1 line multiplexer, if we have two, let me say, digits, two numbers, A and B, each one of them is 4 bits. As you can see here, A from 0 to 3 to A3 and B from 0 to A3. Okay? Now, what we need 2 to power 3, so which is equal to 8 situations. Okay, 8 situations. Now we need 8 gates. It means 8 AND gates. These 4 AND gates for whom? For A, and these 4 AND gates for B. And definitely we need selecting the switch and E now, because we need to three, as you can see here, we need 3 selecting switch, so S01 and E directly, so we have 3. Now you can see here enabling bits and selecting bits appeared here as in a simple truth table. I advise you to apply it at least 1, 2, 3 cases. Okay, apply it and check how it look like the output. Now, multiplexer as a combinational model, sometimes we need more than, let me say, variable in one combinational module. Okay, example here is f x y z. Okay, it's given here in this expression, which is based on the truth table given here. Okay, these are x, y, and this is z. Selecting here from 0, 1 to show which one will be connect. If we look to this truth table, and I advise you to follow the situation in this truth table, we will find that the output, which is 1 at the end, as I mentioned, have 4 min-term expressions. These are this one, which say that x dash, y dash, z, as you can see here, and the other one x dash, y, z dash, the other one, and so on. These represented the first, sorry, because this is 0, the second and the 6th and the 7th min-term, as you can see here. This is the first one, second one, third, and fourth are here. Now, implementing 4 input function with a multiplexer, as you can see here, we go up, we need more switching. Okay, this is when we talk about 8 bits. It means 2 to power 3, which is 8 bits, starting from 0, 1 into 7, 8 bits. Okay, then we need 3 switches for selecting S0, S1, S2. If we apply the same discussion for 4x1 max, we will find the truth table here represented by this one. I advise you to apply it just 1 or 2 of these values and check how it look like the output. What if we have a multiplexer more than one used together? We can use functional unit connecting more than one multiplexer. As example, here this multiplexer for A, which have 2 digits, and this multiplexer for B, which are 4 digits. Okay, and selecting switch here to select RO or R1 for multiplexer max A, and selecting switch here for definitely it will be 2 selecting switch S0, S1, as we discussed before, and we have RO, R2, R3, R4 for B, as you can see. Now the function will connect them. Example, let me give example here. Let's say select A is given 1 here, then definitely R1 will be at the output here, R1, and selecting B given 2, this is 2, this means that R3 will appear across the output. You see here the function will give R1, R3. So in this way we can connect more than one complexer max. Now 3-gate state gate. 3-state gate is another way to construct the multiplexer. It's represented by this, let me say, device. As you can see here, A input, X output, and here we control E. What is the value of E? I tell you it is what is the value of the output. As example, if E is 0 in this one, and this, by the way, this is the code. You can Google it to find its specifications and available in the market. Okay. Now, if E0, then Z will be high Z, and if it is 1, then A will appear across the output, as you can see here. Vice versa for E dash. When it is 0, A will appear across the output. When it is 1, high Z. If we take this to construct 3-stage gates, okay, have a look here. We have here one state gate here for A, as you can see here, and one for B, as you can see here. And this is a select. Let's assume if it is 1 here, okay, then this connected to B, then B will appear here. Let me take another color. If it is 0 here, then this will be 1, and then this means that A will appear across the output. We can use this to construct, max for 4 bits, as you can see here. For each bit, we need one of these devices, as you can see here. Let me summarize. In this topic, we discussed two things, magnitude comparator and multiplexer. For magnitude comparator, we compare between numbers if they are equal, higher than, greater than, or lower than. And we discuss different situation, and we write the truth table, the expression, and then we move to multiplexer, which is data selector. It's like selecting a switch, where we use 4-to-1 selector and 8-to-1 selector and combinational selector, or let me call it max, simply max, and we saw how it worked. Let me stop with this point, and we continue in the next topic. See you.